My name is Michael.
And I'm Kenneth.
Today we'll be talking about basically how we integrate AWS Private CA with SPIRE and base CA at Coinbase. So first, just in case you're not familiar with what exactly we do, we're a cryptocurrency exchange. So we basically deal with like the buying, selling, transferring, and storing of cryptocurrencies. So as you can imagine, like within security infrastructure, it's very important for us to basically like protect users' digital assets, their data, privacy, etc. Especially since we're dealing with like the financial ecosystem. So just a little bit of a background, like what exactly are our security requirements when we're examining some of them. Essentially, we want like a zero trust network. So we want to make sure that basically all communication that's happening within the cluster is properly authenticated, especially since we're running in a public cloud such as AWS. Additionally, we want to be able to do proper node and workload attestation. So what I mean by this is we want to validate the integrity of the workload before we actually give it an identity. So one good example is like node attestation is an EC2 instance, has like a instance identity document that has a signature associated with it. You can actually validate that against the AWS CA. And then if that checks out, then that means it was actually provisioned by the AWS provider. Additionally, we want to leverage industry standards such as SPIFFE. So if anyone has heard of SPIFFE, it is a secure production identity framework for everyone. It basically defines a common format of how you define your X509 and JSON web tokens. And once we're basically utilizing these industry standards, we can easily integrate with open source technologies such as Istio or Kubernetes. And yeah, I'll hand it over to Kenneth to talk about some other security requirements that we have.
Thanks, Michael. So a few other things is that we really want to make sure that private key material never leaves the node it was generated on. So what this really means is we don't want to store private keys into a vault or any other type of secrets manager, but want them dynamically generated at runtime every single time like an instance is starting, right? Kind of going off of this, like we have X509 certificates that we use as service identities, right? So instead of like having traditional certificates that are year-long, we really want to push this like constraint down to as short as we can to 24 hours or even less. So we're a huge AWS shop, so any services that we're building, we also want to be able to leverage and build our platform on top of AWS. We also really want to have isolation between service stages. So even in the case where development and production environments get bridged somehow, we want to make sure that there's strong isolation from an authorization layer as well. And the last one really is that only systems manage key material and people never manage key material. So this really means like any key generation, people don't do this, systems do this. Any certificate issuances, this is all done through attestation and no people are involved through this process. Cool. So let's go over kind of like a high-level overview of Coinbase's public key infrastructure real quick. So this is just a single region, example of a single region, but this is kind of broken down into 3 distinctive layers. On the very top in red, these are our root certificate authorities. These are managed by Coinbase and are completely offline. In the middle, these are intermediate CAs that are managed by AWS Private CA, and these are online. And then on the very bottom, these are actually subordinate CAs that we issue from AWS that our control planes actually take care of and manage. So our 2 control planes are SPIRE and base CA, which we'll talk about in a little bit. But kind of going back to the top as far as like the roots go, as far as like actually being able to build the chains out and sign, what we actually do is we have a specific key generation process where if we determine like, hey, for these intermediates, which chain do we want to build, we take that CSR, we send it up to the root CA and use that private key to sign. But using those private keys, we actually have do this within a Faraday cage in a secure environment to make sure all key generation for our roots, as well as any signing processes, are completely isolated and in a secure environment. The thing that we do actually a little bit different, though, is on the very bottom, we kind of talked about our control planes being able to manage subordinates. So instead of most customers actually issuing certificates directly from private CA, like entity certificates, we actually issue subordinate certificates, and we use these subordinates to then issue downstream downstream entity certificates. So we talked a little bit about base CA and SPIRE, but kind of what are they, right? So base CA is actually an open source project we just released yesterday. It's a gRPC service that's used as a PKI management layer to really be able to issue a lot of short-lived certificates at scale based off of very predefined scopes. And I'll hand it over to Michael for SPIRE.
Yeah, so SPIRE is basically like an open source project. It is a spiffy runtime environment. It is essentially responsible for being a control plane that issues X509 and JSON web tokens to services. And it basically comes with node and workload attestation out of the box as well.
Perfect. So we'll go over through a few use cases at Base CA real quick. The biggest one really is X509 client authentication. So instead of having basic auth to do authentication for things like Amazon MSK, which is their managed Kafka service, MongoDB, and even macOS is something we're looking at supporting in the future, is we're going passwordless and being able to generate short-lived certificates, short-lived identities using X509 certificates to do authentication. For non-MTLS workloads, we also support host-level termination. So instead of using ACM traditionally on the load balancer and kind of like unencrypt traffic from the load balancer to the host, we can also dynamically generate key material and certificates on the entity host for you as well. We also support code signing. So code signing is a little different in this use case where instead of having one really long-lived private key and certificate that does the signing and validation process, we can dynamically generate different code signing certificates, but then on the validation side, we can validate the entire chain. So you actually can use different private keys to sign, but still validate it on the other side. And then this is something that we are looking to support within the next quarter or two, but being able to issue SSH certificates through the service as well. Cool. So just going through a few benefits of ACA real quick. The biggest one is really the ability to protect the issuance of certificates based off of scope, right? So as far as scope, it means which environments are you able to issue from, which chains are you able to issue from, which extended keys you have, common name, subject alternative name, certificate validity, and a whole lot of other things, right? So we have a very tight predefined scope of what you're able to issue, so you can't actually issue something that shouldn't be your identity, right? The next thing is for these service accounts that actually issue certificates, we don't say that, hey, just because you have those service account credentials, you're able to issue these certificates, right? Like Michael mentioned earlier, we do something called node attestation, where we actually ensure that the client or the server that's actually making that request is saying that, hey, we know the identity from you based off of attestation data, and then because of this, plus your kind of service account credentials, then authentication goes through. Out of the box, this is just like a gRPC service that integrates with upstream CAs. So we support multi-cloud, multi-region, on-prem out of default, as long as you have network connectivity and you're able to make gRPC requests. We're also compatible with Nitro Enclave. So because this service manages so many subordinate CAs or has ability to manage many subordinate CAs in memory, what we want to do is we want to make sure that this process is run within an enclave, so that even in the case that there's an underlying compromise for the server, for this service, nobody can actually read the private key material that's used for signing. Also, this is a really cool one, but there's no quota limits on the number of certificates issued. So because we're issuing hundreds of thousands of certificates a day, we want to make sure that we can scale. But if you issue certificates directly from private CA, you run into quota limits. But in our case, because we're doing all the signing downstream, you don't really have to worry about this, and it saves you a few dollars as well. Cool. So just going through a brief example of the architecture for Base CA for how you can issue a certificate, right? So we have a client. Client makes a request to our control plane, sends a certificate signing request with the service account credentials. We'll authenticate to RDS. We'll validate the scope with that service account credentials. In addition to that authentication, though, we also attest the identity of that client, right? So we make sure that whether it's the IAM role it has, security groups, tags, et cetera, it actually matches what we expect for that service account, right? If we actually don't already manage that subordinate CA for which CA that client wants to issue from, we'll issue a subordinate CA from private CA, we'll store it within memory within Base CA, and then we sign it in memory and send it back to the client. One additional thing, though, is that because we're not issuing certificates directly from private CA anymore, like entity certificates, we want to keep a relationship between the end entity and the subordinate CA, right? So we actually maintain this data and the metadata, stream it through Kinesis Firehose and store it in S3. So in case that you need to perform any revocation in the future, we have a mapping that you can kind of search through Athena or whatever other platform you want to. So if you want to take a look at just the bottom left, this is just an example file system directory of what Base CA might look like. As you can see, it manages multiple subordinate CAs, part of multiple chains. Over there. Part of multiple chains. So it kind of gives you the flexibility of saying that, hey, we can plug into many, many different environments for upstream private CAs and kind of still issue from wherever you want. Cool. And I'm going to turn it over to Michael for SPIRE.
Okay, thank you, Kenneth. Okay, so now let's talk a little bit about SPIRE and how we utilize it. So what are the use cases for SPIRE itself? First and foremost, basically service-to-service authentication. So now that we're able to basically provision X509 JSON web tokens to services, we can now properly authenticate them. And additionally, once we have that identity foundation in place and everyone has their own spiffy ID, then we can do authorization layer on top for more fine-grained access as well. Additionally, it provides identities for both EC2 workloads and also Kubernetes. So this is very important for us, as right now we're basically migrating from EC2 into Kubernetes. So we want to make sure that basically we're issuing the same format of identities to both workload types so that they can seamlessly communicate and authenticate with each other. Also, this basically lays the foundation for service mesh. We can easily integrate with a service mesh such as Istio so that we can roll that out in the future as well. And yeah, just to show an example of how service-to-service authentication actually looks like on one of our workloads. On the left here, you have an EC2 node with a SPIRE agent container. This container basically reaches out to SPIRE server, which I'll get into in a moment. And when the workload A is communicating with workload B, it basically needs an X509 certificate that it wants to use for that outgoing call. And workload A will basically communicate over Unix domain socket locally, UDS for short, to the SPIRE agent to fetch that X509 certificate and basically use it for the outgoing call. Then on the workload B side, it basically fetches the CA from its own local SPIRE agent and can check the validity of that particular X509 certificate. And if everything checks out, then it will be properly authenticated and they can communicate with each other. And what are some of the benefits of SPIRE, right? Why do we actually want to use it? Basically, like Kenneth was mentioning previously, provide short-lived identities out of the box. It'll handle the rotation for you of identities, private keys, etc. So this is really good for us. It has node and workload attestation out of the box. So like I mentioned previously with the EC2 instance identity document verification, it will actually do this for you. And it also has other plugins for different workload types, such as Kubernetes, to check the authenticity of a pod running against the Kubernetes API server. Whoops. Also, yeah, it easily integrates with AWS Private CA. So it has a plugin to basically communicate with that service, so we don't have to maintain or implement that as well. So that's easier for us to manage. And like we mentioned previously, this also supports multi-region, multi-cloud. So you can deploy SPIRE in a variety of different regions, clouds, like in AWS, on-prem, etc., but still have them basically go up the same chain of trust up to their root CA and be able to basically communicate between all of them. Authenticate between all of them. So now let's take a look at basically the SPIRE architecture. So how exactly does it look like, right? What are we running here? So as you can see here at the very top, this is essentially what Kenneth was mentioning previously. We have our root CA, which is offline. We have the intermediate below, which is in the private CA service. And down here, what we're going to do is basically introduce a root SPIRE server. This root SPIRE server is also a CA. It fetches its own CA from that particular intermediate. So it has a path length of 1, meaning it can still issue one more CA downstream. And it has an RDS layer for its own internal state management as well. And at the very bottom, we basically introduce a main SPIRE server. And this main SPIRE server is also a CA that it fetches from the root SPIRE server. But it has a path length of 0, meaning that it can only issue end entity certificates and no more CAs. So now let's take a look at how this integrates with the service and what are the benefits of this architecture. So right here on the bottom right, we have an EC2 node. So as you can see, this was the previous one that I showed. You have the SPIRE agent right there. When the EC2 node is actually coming up, that SPIRE agent will make a request out to the main SPIRE server. Here is where the node attestation will happen. So main SPIRE server will validate basically the instance identity document of that particular EC2 instance. If that checks out, then the main SPIRE server basically trusts it as a valid EC2 node. Then the SPIRE agent will go ahead and sync identities locally, for example, in the case of X509. So it will actually reach out to the main SPIRE server to sync those identities. And depending what is stored in the database for this particular workload, it will fetch those corresponding identities. And these are typically registered asynchronously, basically through Amazon EC2 tags, for example, like defining the project, workload, service, etc. So once SPIRE agent has those identities available locally, how does the workload actually get them, right? So if the workload needs an X509 certificate, for example, it will communicate with that SPIRE agent over that Unix domain socket. And here, something called workload attestation will happen. So the SPIRE agent will basically look at the incoming PID of that particular workload and check against the proc folder to see what user and group it is actually running as. And if that matches basically the registered entries in the database and the identities that SPIRE agent has available locally, then it will be able to actually give it to that particular workload. And then it will be able to go ahead and basically utilize that for any outgoing calls. So this is basically known as the nested architecture that you see here. If you ever go on like spiffy.io, you'll see that they refer to this as nested architecture, where you have multiple SPIRE servers. And what are some of the benefits of this, right? Like, why do we want to run it this way? So basically, only the root SPIRE server integrates with Private CA. So the communication between that AWS service only happens between that root and AWS PCA. And the benefit of that is basically we only need to issue CA for the root. But all the downstream basically and entity certificates are all happening through SPIRE. So this heavily reduces our cost as well because we don't have to store all of those in Private CA. And from a reliability standpoint, also the root CA is valid for 7 days. So if there's any blip in, the uptime of the private CA from AWS, then we can still continue running up to 7 days as well. Also, finally, like the main benefit of this architecture is that we can actually shard out the main SPIRE server very easily. So as you can see here, like the main traffic is happening between the main SPIRE server and the EC2 nodes because they're continuously scaling up and down. Identities are constantly being provisioned and rotated for all of our workloads. So we can basically shard out and horizontally scale out the main SPIRE server based on which AWS accounts require more identities or which Kubernetes clusters require more identities, so we can basically scale that out. And the traffic between the main and the root is very minimal because the main CA is valid for 24 hours, so it only needs to communicate with the root once a day, essentially, for its own refresh. And yeah, so basically due to this allows us to really basically scale out and shard out the main SPIRE server depending on where that particular traffic is. Okay, so now to conclude, so as you saw here, like AWS Private CA is very powerful for us. Essentially, as you saw here, like all of the CAs that we're using and provisioning all go back up to those root CAs. So, anywhere we shard out to, for example, in the SPIRE case, like Kubernetes, EC2, etc., they all link back up to that same root so they can still, authenticate and communicate with each other. So Private CA allows us to build out that entire authentication mechanism for our clusters. And yeah, Base CA SPIRE helps build out that zero trust network. Essentially, we're able to provision identities to our workloads and properly authenticate with everyone.
Yeah, so Private CA also really enables multi-cloud and enables resiliency. So we don't really want to have to manage kind of like private key material for intermediates directly and manage an HSM. So Private CA really helps us, help with the reliability as well as security from that point of view. And the last one is that Coinbase Base CA is open source as of yesterday and in beta. So if you're interested in kind of like issuing a lot of short-lived certificates for client authentication, code signing, SSH certificates in the future, go check it out. And would love your feedback. So yeah. Well, yeah, thank you so much, folks. Really appreciate your time here.